In this last video, I want to highlight some trig examples since we haven't looked at any of those yet thus far. But before we do that, I just want to highlight this table right here. This is taken from our textbook. This is just a table of general integration formulas. And this is really just kind of a shortcut for using integration by substitution for simpler cases. So if I look at, say, this example right here, if I was integrating e to the a times x, so if I have just a constant times x, I can take a shortcut there and write that as 1 over a times e to the ax power, and then of course plus my constant of integration c. I have no strong feelings about whether or not you use these. Personally, I don't use any of these. I just kind of use substitution as needed for every single problem. I don't really like to memorize formulas, so I don't use these very often, but they're there if you would like to use them. So we're going to hop into some examples here of some trig integrals. So here I want to evaluate each integral. First up, I have cosine cubed x times sine of x dx. I would like to integrate this function. Here it might help to remember that when we write cosine cubed x, what that really means is cosine of x cubed times sine of x dx. And I think once we write it like this, it becomes a lot clearer for us to say, okay, I know exactly what our u should be, that inside function. That should be our cosine of x. So I'm going to take u equals to cosine of x. Du, the differential derivative of cosine, would be negative sine of x times dx. And I see, okay, I've got this negative sine of x dx right here. The only difference right now is this negative sign, so I'm going to go ahead and multiply by negative 1 to get rid of that, and that will leave me with opposite du is equal to sine of x dx. So here is my u, this is going to be u, and then this part right here, this is negative du. So I'll factor that negative sign out first right away. Negative times my integral. Here I have u to the third du, and I've written this in a way now that is entirely in terms of u. This allows me to just use my power rule here. So let's see, I will add 1 to my power. I've got u to the fourth divided by 4 plus my constant of integration c. But if I started with something in terms of x, I'd like to end with something in terms of x. So here this would be negative cosine x to the fourth power over 4 plus c. Or perhaps more commonly you would see this written as negative cosine to the fourth x over 4 plus c. Either one of these would be perfectly fine. Next up, we have the integral of secant squared 4x dx. Here, this one might be a little bit tricky, but I see this 4x. You might need to know here in this case that if we integrate, say, secant squared x dx, this is equal to tangent of x plus c. So you might look at this exponent right there and think, oh, that kind of looks like cosine cubed x, but remember that the derivative of tangent is secant squared, that we have this kind of relationship between tangent and secant squared. So we're not going to need to use secant of 4x as our u. We're just going to take this inside part right here as 4x. That part will be my u. So u will be 4x du. Derivative would be 4 times dx for our differential. And I see, okay, this piece right here, all I really have left over is this dx. So I need to get rid of this 4. Let's go ahead and multiply both sides by 1/4 in order to do that. So these two cancel. I have 1/4 du is equal to dx. So when I perform my substitution, this is going to be my u, and then dx, this is going to be 1/4 du. So I will factor out the 1/4 right away. So I've got 1/4 times the integral of secant squared u du. And now I can look at that and say, okay, well, the antiderivative of secant squared u, that's going to be tangent of u, and I forgot my 1/4, didn't I? So the 1/4 times tangent of u plus c, and then we'll just take 4x, plug that in. So I should end up with 1/4 times tangent of 4x plus c. Here is my antiderivative. Just a couple more I'd like to look at here. Next, I have the integral of x times cosecant x squared times cotangent x squared. Here, this one's a little bit tricky because we have a lot of multiplication happening here. Here I've got really 3 factors. I've got x, I've got cosecant x squared, and then I've got cotangent x squared. So it might be difficult to remember or to pick out what your u should be. But here you may want to remember that, hey, the antiderivative of cosecant x cotangent x dx, and here's where that table might come in handy. If you want to, I would go back and use that, hey, cosecant x cotangent of x, that antiderivative is negative cosecant of x. So I'm not going to use the constant multiple part. And in this case, we actually can't because we have x squared rather than just a constant times x. But I'm at least thinking about this as my general antiderivative. So this is negative cotangent of x. Oops, negative cotangent or negative cosecant? Negative cosecant, excuse me. Negative cosecant. Negative cosecant x, and then, of course, plus c. So here in this case, we have to recognize that the piece that's inside of cosecant and cotangent is the same. It's x squared. And keeping this piece in mind, this is our antiderivative. I know that I want to make my substitution. Eventually, I would like my substitution to look like cosecant u cotangent u du. That's my goal, because if I can make it look like this, then I can say, okay, we'll behave exactly like the integral of cosecant x cotangent x. So, okay, in that case, oops, and I just erased it, our u should be whatever's inside of cosecant and cotangent. And lucky for us, we have the exact same thing. We have got x squared inside of both of those two functions. So we're going to choose that to be our u here. So u will be x squared. Du then will be 2x dx. So all right, let's look at this. Here's u. That's x squared, so I have u here, and I have a u here. And then du, well, I've got x dx left over. So I don't have this 2. Let's go ahead and get rid of that. So I'll multiply both sides by 1/2. So I have 1/2 du is equal to x dx. So let's see if we can do our substitution. The 1/2 I'm going to factor out right away. 1/2 times the integral. I should have cosecant u times cotangent u du. And now I say, hey, this antiderivative looks exactly like this, except I'm using u instead of x. So I know that it's going to behave exactly the same way. That 1/2 times, negative, let's say negative 1/2 times cosecant of u plus c, and then we'll take our u and plug that back in. So I have negative 1/2 times cosecant of x squared plus c. Here is our indefinite integral. One last example that we'll look at here. This time we have a definite integral. I have the integral from negative 2 pi to positive 2 pi of cosine of t over 8 dt. So here in this case, our u is going to be this piece right here, t over 8. So u should be t over 8, which means that du, derivative or differential, will be 1/8 times dt. So this piece right here, t over 8, that's going to be my u. The only thing I really have left over is this dt. So I'd really just like dt, which means we need to get rid of the 1/8. So in this case, the way I'm going to do it, I'm going to multiply both sides by 8. So I have 8 times du is equal to dt. So when we make our substitution, I will factor the 8 out right away. 8 times the integral, I'll have cosine of u du. And then remember, it's kind of up to you if you want to change your limits of integration or not. I'm a big fan of changing your limits of integration, so I'm going to go ahead and do that. Oops, and I didn't leave myself a lot of room here, did I? So when t equals, we'll start with 2 pi. U is equal to 2 pi over 8. This is equal to pi over 4. So my new upper limit of integration is pi over 4. And then similarly, oh boy, okay, let me erase this right here. When t equals negative 2 pi, u is equal to negative 2 pi over 8 gives me negative pi over 4. So my new lower limit of integration is negative pi over 4. So I'm trying to evaluate this definite integral. I can kind of forget anything I had in terms of t from earlier. So let's see, constant multiple of 8, that's just going to come down. Antiderivative of cosine of u, that should be sine of u, and I'd like to evaluate that at pi over 4 and negative pi over 4. So this is really 8 times sine of pi over 4 minus 8 times sine of negative pi over 4. And then let's see, pi over 4, that lives in the first quadrant. Let me just sketch that out real quick. This should be 45 degrees. Here's pi over 4. And then at this point right here, you would be looking at the point radical 2 over 2, comma, radical 2 over 2. So that means I should have 8 times radical 2 over 2, since sine represents the y-coordinate. Minus over here, this time I'm working with negative pi over 4. Remember, that means I'm living in the fourth quadrant over here. So it'd be radical 2 over 2, comma, negative radical 2 over 2. So minus 8 times negative radical 2 over 2 is our y value there. And then let's see, I've got 8 radical 2 over 2 minus negative 8 radical 2 over 2. So let's see, I should have 4 radical 2 plus 4 radical 2 gives me 8 square root of 2. Here is my solution. So I just wanted to wrap up by looking at some trig examples here, since we hadn't touched on any of those in the prior videos. Again, you can use that integration table if you would like. I don't require it. I don't think it's necessary, but it's there for you if you want it. And unfortunately, ladies and gentlemen, that's it. That is the end of Calculus 1. And I'm getting a little choked up here. I hope you've learned a little bit of calculus and a lot about yourselves along the way. But in all seriousness, I wish you all the best of luck. I hope you've enjoyed this class. I hope you've laughed at my very funny jokes. If you have questions between now and the final exam, please feel free to reach out for me. Take a look at that final exam review. It should be posted up on Canvas. And best of luck to you going forward.